Okay, so in this video, I'm going to talk about the Towers of Hanoi game. So this isn't really, or puzzle I suppose, this isn't really going to be a video about algorithms per se or math per se, but we will use this as an interesting example. So you may have already seen this when you took discrete mathematics. So here up on the screen I have basically the game board. So what I have is three towers, right, or pegs, dolls, whatever. And those three things, right, basically I have on top of that these different disks that can be set. And there's a certain number of these disks, and I can move them between those pegs. My goal, right, in this game is basically say, okay, I have this initial setup. Here I have basically all of my disks on the left, and I might want to try and move them all to the right-hand side. And so there's a puzzle where I'll have to follow these rules and gradually move those disks from the left side to the right-hand side. So there's three different rules. First of all, if I want to move a disk between those towers, between those rods, I can only take the topmost one, right? I can't reach to the bottom and take something from there. I only have access to the one on top. Second thing is that I have to move only, or I can move only one disk at a time. I'm not allowed to pick up two or three or four. I have to move only one thing at a time. The last rule is that I can never place a smaller disk on top of a larger disk. It's supposed to be a tower, right? You're building upwards. So those are the rules of the game. The way it's played is basically you pick up a valid disk from one of the towers you have available, you have to pick from the top, and place it onto another tower, provided that is a valid location to place it, meaning you're not placing it onto something that's smaller than itself. So that's our game. Maybe to think about algorithms analysis for a second, we could think to ourselves, hey, you know what would be neat? It would be neat to write a growth function that models the number of moves that are necessary for a tower of specific size. So our problem size, right, could be something like the number of disks, right? How tall is the tower? And then based on the tower, can I predict, right, or model how many different moves, right? How many times do I need to move a disk in order to move that entire thing on the left-hand side over to the right-hand side? So algorithmically, that's what we can think about in the back of our head, and later we'll look at writing an algorithm to do that, and then also writing a growth function to model that algorithm. So this is the game. Let's maybe try working through a small solution for it first. So here I have basically the start, right? So everything's on the left versus the end. Everything is on the right. So how would I play this game? Well, I could start with the following. I could say, okay, my tower, right, that I need to move over, I can do something like move this top piece over here. I also have the choice to move it to the middle, but just for the sake of playing through the game and the fewest number of moves, I'll move it to all the way to the right. So I put the smallest piece over there. That's fine. And that gets me this picture over here. So now my smallest piece is over here. My two remaining pieces are on the initial rod. So it looks good. Following the rules, playing the game, I've made a little bit of progress towards my goal of moving all the disks to the final tower. Then I can maybe move this one, right? So I can move my middle piece to the middle rod, or the middle tower. Make a little bit, we're not really making progress there, but we're moving things around. So hopefully it gets us something. Continue to play this game. Right now everything's spread out, and in this case, right, we can think to ourselves, oh, our final goal is to move the tower in its entirety to the right hand side. So what can I do now that everything's spread out? I have a bunch of flexibility now. What I can think about is oh, hey, I can move this small one on top of the middle one, right, and get basically a too tall tower there, and that frees me up to move the largest piece to the final tower. So there, right, all of a sudden I made some concrete progress. Right, the resulting picture over here has basically the two pieces in the middle, which are still out of order, right? I want everything to be on the right-hand side. But also, the biggest piece is now on the final dowel, the right-hand side one. So I've actually made progress towards my goal. Okay, so that's good. Now I only have to worry about these two. Well, over here, the rules obligate me to make only one move, so I move the smallest one over here to the left-hand side. Gets me this picture over here. Everything's spread out again, and now you can maybe see it's pretty easy to reassemble this thing. I move the middle token to the far right, and then the first piece, right, the last disk, to the very top of that last tower. And so I get at the end all these things stacked one on top of each other. So that's the game. That's how I would solve a case of size 3, right, with 3 disks to move over. So maybe stop and think for a second. Is there any kind of general rule or mechanism behind the scenes here that we could use, right? Is there any sort of algorithm that we could maybe have to solve this? So think for 1 second. So here's an idea. What if we said that this was comprised mainly of 3 steps? The first step would be to move a n-1 size tower from the first dowel to the middle del. Right, so this gets moved from here to here. That's maybe one step, because that frees me to move the final disk, right, the biggest one. And then the final disk, right, we said gets moved to that final tower. That would be maybe one thing that I do, afterwards, right? So my first move is to move n-1 disks from the first tower to the middle tower. Then my second move is to move the biggest disk from the first tower to the last tower. And then the last thing I would do is move the smaller n-1 tower from the middle to the final position, right, on top of the largest disk that I just moved. So if I do those two things, right, move an n-1 tower, move a disk, move another n-1 size tower, then at the end of the day, I'll have migrated all my disks from the first tower to the last one. So that's the idea we'll stick with, and that'll give us some sort of algorithm that we can use to solve this problem.